So let us start a new topic today, probabilistic retrieval model. Probabilistic retrieval model. So last class we have seen about your vector space model, and also we have seen calculations on vector space model. So vector space model, there we need to mainly find out the cosine similarity. So in order to find out the cosine similarity between the documents or between the document and the query, first we need to know term weighting, and also we need to know TF IDF, IDF where it stands for inverse document frequency, and finding the dot product, and also finding the length of the document or length of the query. So after that, we have probabilistic retrieval model. So in probabilistic retrieval model, we are going to review the basic probability theory. Okay, give me just 1 second. Hey, class load here. So we will be having a brief review on probability theory. The normal probability theory, which you have already come across in your mathematics and other papers also. So here, first one is random variable. Random variable, what is a variable, right? So variable is just some random um, representative where we use for some computations. So a variable A represents an event. Here, a variable A is going to represent an event, a subset of space of possible outcomes. And we have random variable. Random variable is a function from outcomes to real numbers. So this is, you can just go through, and for all the probability of the event, it will be, the value will be less than or equal to 1. So 0 less than or equal to probability of variable A less than or equal to 1. Then suppose if we have two events A and B, then the joint event of both the events A and B is represented by P of A, B. P of A, comma B. So this represents the joint probability of the two events A and B. And conditional probability is represented with this. This is known as conditional probability. So this expresses that the probability of an event A given that the event B occurred. So probability, conditional probability of A and B is normally it means that the probability of event A given that event B occurred. So this is conditional probability of A and B. Then the fundamental relationship between the two joint and conditional probabilities, they are represented by chain rule. So the relationship between joint probability and conditional probability, they are represented by using chain rule. So let us see chain rule. So this is joint probability, right? P of A comma B. This is joint probability. Joint probability is also represented by A intersection B. So A intersection B. Then this is A intersection B is given by conditional probability of A and B dot product with probability of B and conditional probability of B and A. When you say B and of A, this means that just the opposite of this one. So when it is a conditional probability of B and A, it means that probability of event B when that event A occurred. So this one. So the joint probability of A and B is equal to conditional probability of B and A dot product along with probability of A. So this is chain rule. Chain rule. So the probability of joint event is equal to the probability of one of the events multiplied by the probability of other event conditioned on knowing the first event happened. Okay, so on knowing that means probability of B and A, conditional probability of B and A, it means that probability of A is already happened. Okay, and this probability of A, it is already occurred. This event is already occurred. We know this event, and we are going to condition this probability of B on A. Condition probability of B on A. Okay, multiplied by probability of A, which is already known. So this is chain rule. Once again, probability, joint probability of A and B, it is also equal to intersection probability of A intersection B, and this is equal to these two probabilities where it is multiplied by the probability of other event condition on knowing the first event happened. And complement of an event, probability of complement of an event, it is given by the condition probability of B on complement of A multiplied by probability of complement of event A. Then partition rule. Partition rule, it says that if an event B can be divided into some exhausted set of disjoint subcases, then the probability of B is the sum of the probabilities of the subcases. The probability of B is the sum of the probabilities of subcases. Okay, so this notes you can just go through once. These are the normal set theory, probability and set theory, which you have already learned. So in partition rule, it is given by probability of B. Probability of B is the sum of what? Joint probability of A and B and joint probability of complement of A and B. So this is sum of these two, it gives probability of B. So this is known as partition rule. So first one is what it is known as chain rule. Chain rule is where just we find joint probability of A and B, and complement of an event is given by this formula, and partition of rule. So probability of B, it is given by joint probability of A and B plus joint probability of complement of A and B. Next, Bayes rule. So Bayes rule is what we are going to use in all our computations in this probability retrieval of information. So Bayes rule, it is condition probability of A and B. It is given by condition probability of B and A multiplied by probability of A upon probability of B divided by probability of B. And this can also be expressed in this formula. Okay, summation x belongs to event A and complement A, probability of B and x, and multiplied by probability of x. So here we use a variable x. So this initial is estimate, we are going to find out the initial estimate of how likely the event A is happened when we do not have any other information. So this is known as prior probability. So prior probability P of A is nothing but it is an initial estimate of an event A being occurred when we do not have any other information. So when we do not have any other information, when you just find the probability of an event as an initial estimate, then that kind of probability is known as prior probability. And this condition probability, this one, here also we find this posterior probability. This is also known as posterior probability. So posterior probability is nothing but after having seen the evidence B. So after event B is already occurred, based on the likelihood of B occurring in the two cases that A does or does not hold. So A, we are going to find B being known and A, it may happen or it may not happen. So that kind of probability is known as posterior probability. So B, this probability, this evidence is being already occurred and we know this evidence. And based on this evidence, this probability of A may occur or A may not occur. So this kind of probability is posterior probability, and prior probability is where when we don't have any other information and we are just finding an initial estimate of how likely the event A may occur. So that is posterior probability. So once we come to the computation part, you will understand how to calculate all these things. These are all the review for your probability theory or set theory, probability theory and set theory. Then odds of an event. Odds of an event. So this is also given by this odds of event A is given by probability of A divided by probability of complement of A. And also complement of A, it can be written by 1 minus probability of A. So this is odds. Odds of an event. Odds of an event. Then probability ranking principle, PRP. Probability ranking principle, PRP. So for this, here for any query Q and for a given document B in a collection. So let us see this statement. Let us see this statement. For a query Q and a document B in the collection, let RDQ, D is document query, Q is query, be an indicator, a random variable that says whether D is relevant with respect to a given query. So we are going to check D, the document D is relevant with respect to the query or D is not relevant with respect to the query. So if D is relevant, we are going to put 1, and if the document D is not relevant with the query, then we are going to represent by 0. So that is what the statement says here. That is, it takes on a value of 1 when the document is relevant. So when the document is relevant to the query, it takes the value of 1 and 0 otherwise, and 0 otherwise. So this probability ranking principle, it is denoted by R, or it is can be denoted by this one. So normally For relevant, we represent by R. For relevant, if it is a relevant document, we represent relevant as R. So using the probabilistic model, you can see here if it is relevant, then probability R equal to 1. So when R equal to 1, it means that this So this document is relevant with respect to the given query Q. So R equal to 1, it denotes that the particular document is relevant with respect to the given query Q. Okay. So probability R equal to 1. If you write like this, then this is known as probability ranking principle. Okay, if it is 0, then the document is not relevant to the query. So another terminology is that 1 by 0 loss case. 1 by 0 loss case, this also comes under probability ranking principle. So in probability ranking principle, what does it say? If a particular document is relevant, it is represented by 1. That means R equal to 1. And if it is not relevant, then R equal to 0. In this PRP principle, we lost the point for either returning a non-relevant document or failing to return a relevant document. Thus, the binary condition where we are evaluated on our accuracy is called 1 by 0 loss. So, when the 1 by 0 loss case, it means nothing, but suppose when it is relevant, we are going to just write the probability for being relevant, R equal to 1. So in this case, we do not return the non-relevant document. So we do not return, when it is say 1, R equal to 1, we do not return the non-relevant condition. Okay, non-relevant document we do not return. And suppose when R equal to 0, then we do not return the relevant document. Clear? So it has two sides. It has two sides. When I say R equal to 1, it's going to return only the relevant document. Suppose in the collection, if there are some non-relevant documents, then it is not going to return the non-relevant document. And again in PRP, if I say R equal to 0, then it's going to return only the relevant document. And sorry, non-relevant document. It's going to return only the non-relevant document, and it does not return the relevant document. When I say R in PRP, R equal to 0. So here we are losing some point, right? So either when in one condition it does not return the non-relevant document, and in another condition it does not return the relevant document. So this binary condition we represent as 1 by 0 loss case. 1 by 0 loss case. So the goal for one this such condition is that it is to return the best possible results. Best possible results for k documents, and for any value of k user chooses to examine, the PRP then says to simply rank all documents in decreasing order. So, this probability ranking principle, they are going to rank the documents. They are going to rank all the documents. Okay. So, for this also, we will see all the examples so that you will clearly picture out this condition. Again, another one is optimal decision rule. Bayes optimal decision rule. Here it says that the decision which minimize the risk of loss is to simply return documents that are more likely to relevant than non-relevant. So in Bayes optimal decision rule, what does it say? This will minimize for the risk of loss. The risk of loss. So 1 by 0 loss case So this is going to reduce the condition for being lost. Okay, that how? By returning the documents that are more likely relevant than non-relevant. So what is more important in our retrieval method is that we are going to return the relevant document, right? So we do not give much importance in returning the non-relevant document. So we give more importance in returning the relevant document. So of Bayes optimal decision rule, what does it do? It reduces the risk of loss. The risk of loss in the sense it returns more relevant document rather than returning non-relevant document. So here you can see down D is relevant even only if probability of R equal to 1 is greater than probability of R equal to 0. So this means what? Mostly we are going to return the relevant document. We are going to return only the relevant document. So this condition is Bayes optimal decision rule. Bayes optimal decision rule does what? It does minimizes the risk of loss, and we are returning only the relevant document rather than returning the non-relevant document. And PRP with retrieval cost. PRP with retrieval cost. So C1, if you consider C1 as the cost of not returning a relevant document, C1 is the cost of not returning a relevant document, and C0 is the cost of returning a non-relevant document. C0 is the cost of returning a non-relevant document. Then PRP says that for a specific document B and for all the documents DDAS not yet retrieved. DDAS means document not yet retrieved. And DDAS is the document not yet retrieved. Then D is the document to be retrieved. So here it given C0, which is the cost of retrieval of a non-relevant document, multiplied by probability of returning a non-relevant document minus C1 into probability of returning a relevant document is less than or equal to C0 multiplied by probability of returning a not relevant document, and this document is not yet retrieved, minus C1 into probability of returning a relevant document of not relevant, document which is not yet retrieved. So this is the condition. So C0 into P probability of non-relevant document minus C1 into probability of relevant document is less than or equal to C0 into probability of non-relevant document for the document not yet retrieved minus C1 into probability of returning relevant document for the document not yet retrieved. So this is PRP with retrieval cost. PRP with retrieval cost, the formula is given here. Next one is binary incidence model. So binary, as you know, will have two numbers, mostly 0 and 1. 0 and 1. So binary, when I say binary, it is also means Boolean. So binary is equivalent to Boolean. Documents and queries are both represented as binary terms incidence factors. So this is already done in your Boolean retrieval model. So we know Boolean representation, construction of the Boolean matrix, and construction of binary term incidence matrix. So here in binary incidence model, we will be representing as binary term incidence vectors. Vectors. There we have represented as matrix in binary retrieval, Boolean retrieval model, and in binary independence model, we are going to represent the document and queries as binary term incidence vectors. So that is, if a document D is represented by the vector x vector, okay, by the vector x, which is equal to x1, x2 up to xn. So this is D, okay, document D. So now document D is represented by vector x, which has x1, x2 up to xn, where xt equal to 1 if the term t is present in the document. Same thing, only the concept is same with Boolean retrieval model, where in Boolean retrieval model, we just consider the Boolean matrix representing zeros and ones for the term presence. If the term is present, we in the document we represent by 1. If the term is not present in the document, we represent by 0. The same concept we are using here, but instead of using the matrix here, what we have done is we have done um, the application of vectors. So x vector, if the document D is represented by x vector now. So for this also, if xt will be represented by 1 if the term t is present in the document, and xt equal to 0 if the term t is not present in the document. Now, independence. We use binary independence. So what does independence mean? So independence, it means that the terms are modeled as occurring in documents independently. Hence, the terms are occurring independently in the document. We use the term independence. So the model recognizes no association between terms. So that means the terms are not dependent to each other. That's why we use the term independence. So under binary independence model, we will be modeling the probability of R, D document in the query. That is, a document is relevant via the probability in terms of term incidence vectors. In terms of vectors. Okay. So this particular term, it will be represented by this term now. Instead of this probability, we will be writing as vectors. Probability of R, x vector, q vector. So x vector indicates the document, q vector indicates the query. So just this one we have represented using the term incidence vectors. So using the Bayes rule, one you have done this Bayes rule, we will be rewriting this formula in the form of vectors. So we are writing the formula in the form of vectors for two conditions. First condition for being relevant, and second condition for being not relevant, non-relevant. So R equal to 1, it says the document is relevant. R equal to 0, it says the document is not relevant. The same thing we have represented using vectors. And these vectors for relevant condition and not relevant condition, they so these two conditions are the probability for relevant and not relevant. So first condition is for relevant condition, second condition is for not relevant condition. So since we have only two conditions, either relevant or non-relevant. So if you add these two probability, you'll get 1. So since a document is either relevant or non-relevant to a query, we must have this sum of two probabilities must be equal to 1. This is another condition. So now we will start occupy model. So up to this we have studied the probability review of the probability theory. Now we will start first model, occupy model. Occupy model is very important. We have three occupy models: basic occupy model, improved occupy model, then occupy model with BM25. We have some three occupy models. So let us first start the first occupy model. So occupy model, what we are going to do in occupy model is we are going to compute the term probabilities. The term probability for each term in the collection, in the documents, we are going to find the probability. So assuming if there are no retrieved documents, then probability, this is constant, normally a value of 0.5. When you initially consider there are no retrieved documents, then the probability of term will be a constant value with a value of 0.5. So R is 11 documents and R negative is non-relevant document, R dash. So this is R dash, okay. Above you have a small symbol here, R dash. This is R, this is R dash. So R is for 11 document, R dash is for not 11 document. So this is the basic term weight. Basic term weight is computed using this formula. Okay. So for the probability of the term is given by log n minus n plus 0.5, which is the constant value, and n plus 0.5. So this capital N is same for this one. In last class also we have seen capital N. The capital N stands for total number of documents in the collection. And small n, it stands for number of occurrences of the term T in the document, which means the frequency. Okay, number of occurrences of term T in the document. So you just need to remember this formula for further computation. So first let us see one example. So this is the example, basic term weight. First occupy model, the name is basic term weight. So for basic term weight, I have 6 documents along with some information. So you already know these are called the terms. Again, these are called the terms. So D1, D2, D3, D4, D5, D6, these are called the documents or the document IDs. So total N is what? N is how much? N is how much? N is how much? Capital N is how much?
6.
6. So capital N here according to this example is 6. Now we will start a computation here. You can see the example here. So I have just written the matrix which we have already done in our previous classes. So I'm writing the document IDs here. I have 6 documents, 1, 2, 3, 4, 5, 6, and I have written all the terms here. Cold, day, eat, hot, lot, 9. So this is just it should be 9, N-I-N-E, 9. Here the term this 9. Okay. So 9 all P. So I have written shortly for pour, it is nothing but the porridge. So for this porridge, I have written pour and pot. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 terms and I have 6 documents. Now I'm going to find basic term weight. So this 1.0 is nothing but your Boolean matrix, no? Since we represent in vectors, I'm just writing 1.0, but you can write 1 and 0 instead of writing 1.0. This will be, if it is very confusing, then you can just write 1 and zeros. So first, call is there in D1, so 1. Call is there in D1, so 1. Day is there in D1, day, D-A-Y, day is not there in D1, so 0. So I'm just leaving it, okay. It is there in D1, no, so 0. Hot is there in D1, yes, hot is there. So call, hot, P, porridge. Only these four terms, I'll be writing 1, others all zeros. So call, hot, pea, porridge. I'm writing 1, others all zeros. Similarly for D2 also, D2 it is pea, porridge, pot. Only in these three terms, I'll be writing 1, others 0. So pea, porridge, pot, others 0. So like this, I have constructed the matrix here as vectors. So this since we have come to probability retrieval theory, we are using vectors. That's why document vectors. We have written here document vectors. So up to this construction of zeros and ones, you know, right? Now we will find term weight, basic term weight. So queries can be given like this, or otherwise you can all find out for all the terms. So if the particular query is given it, then you can find only for it. If it is given porridge, you can find only for porridge. But if it is given, if I ask you to calculate for all the terms, then you have to find out for all the terms. So let us check the first one. Wet, cold, it is getting 0.26. This is using this formula, probability of log n minus n plus 0.5, n plus 0.5. So let us see how here. So for cold, log n minus n plus 0.5 divided by n plus 0.5. This is the formula, basic term weight for coal. Now n is 6, capital N is 6, minus 2 is for coal. So let us see from the document, let us see how many coal are there in the collection. So I have one coal here, I have another coal here, so 2 times. So that means you can write small n as 2. N plus 0.5, the constant probability value. Then after computing, you get 0.26. Similarly, for porridge also capital N is 6 for all. I mean, total number of document is 6. So for every computation, you are going to write capital N equal to 6. Now come to the document, you will see for porridge. So one porridge is here, another porridge is here, and one more porridge is here. So 1, 2, 3. The frequency is 3. 3 is written here. Then 3.5 by 3.5, it is 1, log 1 is 0, so you'll get 0. So here for this is for which term? Porridge. For porridge, it will be 0. See down here, the basic term weight for porridge is 0. 0.0 it is written here. Similarly, you can substitute for all the terms and you can find out the basic term weight. So improved ranking we will do tomorrow. Improved ranking is little bit lengthy. Same only here, but we just add one final term weight here. We just add this table and the same formula we are adding R here for 11th document. We are adding R here. See, this is the formula. For basic term width, this is the formula, and for improved ranking, this is the for improved ranking, this is the formula. Okay, calculation will be same, but here since we have two R's and two N's, one R is for relevant and one R is for frequency for the relevant document. Frequency for the relevant document. And this capital N, as you know, this is the number of documents, and small n is frequency for that particular term in the document, and this R is frequency for the relevant document, so here there will be conditions given like this. 2, it is highlighted, right? So this means that document 2 is relevant. Like this, conditions will be given. So if I give only 2 highlighted, 1, see, where is the condition? Okay. For this particular example, document 2 is relevant. Then capital R equal to 1. Since we have only one relevant document, capital R is 1. So I'm writing here capital R equal to 1. Why? Because we have only one relevant document. Okay. And suppose if document 2 and document 4 are relevant. Suppose in this example, document 2 and 4 are relevant, then what will be the value of capital R? What will be the value of capital R? What will be the value of capital R?
2.
2. Yes, good. So, capital R will be 2, like this. So, I'm just teaching you the difference for R and N. Okay, N, it is total number of documents. 11 or not 11, we are going to count all. Okay, so for that particular example, R N value is always 6 because we have only 6 documents, 11 or not. But for capital R, what we are going to do is in the condition, in the equation, they are going to specify relevant document or not relevant document. So for this particular example, document 2 is relevant. So R equal to 1. If I say document 2 and 4 are relevant, then R equal to 2. So for this particular example, document 2 is relevant and R equal to 1. Now, this R, small r is nothing but we are going to count the frequency in the relevant document. So when you calculate for P, this R will be 1 because the frequency in the relevant document is 1. It occurs only one time. So for P, when you calculate, it will be 1. So log 1 plus the improved ranking weight for P. Improved ranking weight for P equal to log R. R is 1 here in our case because P is there in the relevant document one time. So 1 plus 0.5, N will be 6. 6 minus 1. N is 6, R is 1, so 6 minus 1, and N. This N, I'm going to count for P in the document. Okay, so P in the document, it is there how many times? It is there in D1, it is there in D2, it is there in D3. So small n will be 3 here. Small n will be 3 here. Okay. Then again small r, it will be 1 since P is there only in our 11 document. 1 plus 0.5 divided by 3 minus 1 plus 0.5, 1 minus 1 plus 0.5. So check it if you get 0.62. Check if you get 0.624p using the values which I have set now. Okay, so that calculation we will do tomorrow. So you can just go through the slides if you don't understand, and still if you have doubts in calculating for basic term width and improved ranking calculation we will do tomorrow. For basic term width, if you have any doubts in the calculation part, you can ask me tomorrow. Okay, so for today, we will wind up here. So before that, I'll take a roll call. Roll number one,
Present, ma'am.
roll number two,
Present, ma'am.
roll number three,
Present, ma'am.
roll number